Yeah, guys, can you hear me? Any?
Yes, sir.
Yes, sir. Good evening, sir.
Good evening, all. Okay. So last topic, what we have discussed, guys? Can you just tell me? Last topic. Have we completed the Bayes-Sauer's law applications? Numericals.
Sir, we will do resultant magnetic fields.
What, buddy?
Resultant magnetic field.
Okay, okay, okay. Have we started Ampere's law?
No, sir.
No.
Yeah, yeah. So last class, what like we have like straight conductor DY completed? Straight conductor.
Yes, sir.
Yeah, numericals also I think I have completed. Next, put a heading today. So today we'll discuss Ampere's circuital law. Ampere's circuital law. Okay. So
So how many applications were there for the Bayes-Sauer's law?
we have only two, buddy.
Okay, sir.
Okay. One is with the loop and one is with the straight conductor. And but with help of Ampere's circuital law, we have four applications. Today we'll complete those also. Right. Chalo. Put a heading today, Ampere's circuital law. Okay. So here Ampere's circuital law, and it is also known as a ACL. Okay. In general, we call it as a ACL, Ampere's circuital law. Right. Right. So this Ampere circuital law, in the just I would like to give you the just brief things, which is like past classes. I told you that Bayes-Sauer's law is like a Coulomb's law. Okay, Bayes-Sauer's law. Okay, it is like a Coulomb's law. If I say analogy, if I say similarity between electrostatics and moving charges and magnetism, Bayes-Sauer's law is like a Coulomb's law in here. Whereas so Ampere circuital law means ACL is like a Gauss law. ACL is like a Gauss's law, and whereas Bayes-Sauer law is like a Coulomb's law. Okay, so you just have to take it into consideration, and whenever you study Ampere's circuital law, it's like a Gauss law in the moving charges and magnetism. Right? Chalo. So what we do here as like a Gauss law, here what we have to understand is, so we'll actually try to prove the Ampere's circuital law. Okay, so now put a heading Ampere circuital law, and you need to write a statement. What is it? Like a definition, you have to write a statement. So write down the definition for the Ampere circuital law. Definition. Very easy and very important, and we are going to complete today 4 application of it. Very easy applications are there. Okay, no need to worry. I'll do it with a very easy way. Right. Write down now Ampere circuital law. Write down. This is you have to study, you have to remember as it is. The statement you have to remember as it is. Okay, I'm not going to change the statement, and you should not write your own statement here. You have to always write as it is. Write down. It states that it states that it states that integral line integral of line integral of magnetic field induction magnetic field induction B bar around the closed path in the vacuum in the vacuum is equal to is equal to mu naught times mu naught times mu naught times current I threading the closed path, threading the closed path. Very easy and simple, but the statement you have to learn, you have to practice it. So what does it mean actually? He says that here it states that line integral of magnetic field induction B bar around the closed path in a vacuum is equal to mu naught times the current I threading the closed path. What does it mean actually? It is simple. So if I say, let's suppose now there is a wire body, there is a wire like this. Okay, so to this wire I am taking one around this one. Definitely what happens whenever current passes through it, so you will get one kind of like this, right? So here, what is this body? What is this actually? See, inside this there is a current I is flowing. Now if I use right hand thumb rule, current I is flowing. This red color, whatever the red color you see, this is the center of the red color you see, this is a field. So no, the field around this one. So now the field is everywhere. What happens? It is tangential to it. Am I correct? So I'll try to do little bit bigger one so that you will understand. So just give me a minute. Just give me a minute. Okay. A field is like this. RS like this. Can I do? This will be easy for you. Right? See here, what happens here? So if I say this is a current inside this one is I current is flowing. So if I current is flowing through this one, you see this is the center of this wire, and this whatever the shaded area you see, this is nothing but magnetic field around it. So any point, if you take anywhere a small point, if I take like here to here, A to B, this is a small length I'll take, because I initially I used to take a small length on the conductor itself. I cannot take it like this now. I have to take a length on the magnetic field, this loop itself, because magnetic field lines is always makes a loop. So now to this one, magnetic field will be, what is it? Magnetic field is always tangential like this. Magnetic field, what happens to magnetic field is always tangential. B is like this. Okay, because A to B I cannot take. So now you see, let's say this is a small element, A to C is a small element, and magnetic field acting on this one is B, like this, tangential to it. And similarly, the small element on it, which is DL, also acting in the same direction. So this equation, what happens now? Integration of B bar dot DL bar, which is equals to mu naught times current passing through the current conductor. Okay, so this is the equation you will get it with the Ampere circuital law. So this is, we'll use it like a Gauss law we have used, right? EDS is equal to flux is equal to EDS is equal to Q divided by epsilon naught. Like that, it is B bar dot DS bar is equal to I equal to mu naught into I. Let's take this is the equation 1. Here a few things you should always remember. DL is a small element. Okay, a small element, elemental length of magnetic field or magnetic field loop, right? And mu naught, so you know it is a permeability. I is the current passing through the conductor, and B bar, and this is also DL bar. This is a elemental length which is you are taking on the you see the on the field itself.
So DL bar is A to C, right?
Yeah, A to C, but you can say this is a
Approximately
A
equal
to
to the
C.
arc, right?
Yeah, distance from here it is r, buddy.
No, sir. Equal to the arc, so that A to Z.
A to C, what is it?
So the arc, so the length of the arc.
It is arc, buddy. Elemental length or length of the arc, you can say. You can say, no problem.
Imaginary, right? This
It's imaginary only.
magnetic line, okay.
Yeah, it's imaginary only. Because there are so many loops will form, nobody. It's not one loop. There are so many loops. If I just sprinkle, like if a wire is like this, if you sprinkle some of the magnetical, like magnet, what do you call the iron fillings on it, what happens? They'll arrange many loops, right? Not only one loop, there are many loops. But in that one small length, if I consider and if I do the integration, you will get the whole magnetic field at that point. Right? So we'll try to prove it. You need proof? No problem, I'll do the proof, okay? Chalo, shall I move forward? So I'll try to prove it.
So 1 second, sir.
Okay, guys, next, what we do is actually we'll try to prove it. So here, so you can see this is a proper loop. What if there is a improper loop? Improper loop, if it is has, then will you able to get the magnetic field induction? Yes, of course you can do it. So we have to do it with help of Ampere's circuital law. I'll prove it like that only. Right. So if I go a little forward now, see Ray, proof we'll try to do because it is a statement, so we need to prove it. So what is the proof actually I can do? See, I'm taking one line here like this. Okay, inside this there is a current I is flowing through it. Okay, there is a current I inside this one, current I is flowing through it. Now what I'll take here, there is a what do you call a plane, I will take it, okay, like this. Okay, not able to draw. A plane means a imaginary plane, you can take it like this.
So perpendicular to the line.
Yes, buddy, it is perpendicular plane. Yeah, a perpendicular plane you are taking. Now if I see what is happens here, now whenever if I see there are so many loops will form around it like this, there are so many loops will form, right? Magnetic field. So instead of that, what I'll take is one irregular loop I'll take, not the proper loop, but a irregular loop like this. Like this, there is a loop, means it is a closed path. Definitely there is a closed path. Now what is this loop actually do? Here what I'll do is this loop, this is the center. From the loop, actually you see, so from here to here there is one arc length I have to take, which is a, let me say this is A to E arc length, and this length is actually having how much angle? Very small angle, which is very small angle here. Okay, I would actually show a little bigger. So very small angle, I'll take it here. This is here to here, the arc length, which is a E to F. And the length here is, you can see what is the angle it will make, very small angle d theta 1. And here to here, arc length is actually dl1. And this is located with the r1. Okay. In the similar fashion, if I take one more loop here, So which is, let's say, here to here, this is a EFG, let me take, and the angle made here is a d theta 2, and the arc length G to F is a DL2. This is DL1, this is DL2. Okay.
So,
Next.
so d theta 2 is the between G and F, right?
Yeah, G and F, d theta 2, very small angle. Okay.
Okay.
So enough, like this, there are so many loops are there. Only two elements I'll take, and from there we'll try to prove it. So what I'll try to prove is, just before that, I'll try to take, so if I just imagine here, so what is this ray you got? I'll try to take it out, this loop, and I'll show you. Like this one, right? E to F. And this is O. And you have an angle is, how much angle right here? You have an angle is d theta 1, and this is DL1. So what you have here from this triangle, from triangle OEF. Okay, what can I write, buddy? Tan d theta 1, which is equal to, can I write DL1 divided by R1. So you know already here, if I say tan d theta is very smaller one, it is equal to angle d theta 1. Right. Now, one more thing I would like to share here. What is it, buddy? So you know that if d theta 1 is this one, then d theta 1 is equals to what? I'll get it here, DL1 divided by R1. Similarly, d theta 2 is equal to what? I'll get it here, DL2 divided by R2. Yes or no? Similarly, one more thing here, d theta 3 is equals, what can I write? DL3 divided by R3, like that. So many things I can write it. So what is our main consideration here? LHS is a line integration. LHS is equals to integration of B into B bar dot DL bar. Okay. So here B bar dot DL bar. And one more thing I have to say from this one, which is equals to, what is that? Simply I should add it. So B1 dot DL1 plus B2, B bar dot B2 and DL2. So here, before that, I am writing this thing. What I wanted to make it is here. Okay, so these are all perpendicular only. So this will become, okay, here this is a B bar DL. This will become dot product, right? Dot is there. So B DL cos theta, right? So this theta is actually angle between the B bar is parallel to DL bar. So the angle is actually 0 degrees. So what happens here totally? So LHS will become now simply, which is equal to integration of B dl. So if you add up here simply, to B1 dl1 plus B2 dl2, like that. If you add so many, because each element has a arc 1, right? So you are adding it. Then what happens here? Simply, instead of B, magnetic field due to the loop, I told you that what is it, right? Mu naught divided by 4 pi 2I divided by R1 into DL1 plus B2 is equal to, what can I write here? Mu naught divided by 4 pi into 2I divided by R2 and DL2. Like that, you should write so many steps here. So DL2 plus like that, it will be so many steps I can write. Just note down. So chalo guys, shall I move forward?
So 1 minute.
Okay.
Yes, so done. Thank you.
Yeah, buddy. So I'll continue here. Theorem. LHS is equals to, I will continue here, which is integration of BDS, means BDL, you got it, which is equal to, I am writing every time as B1 DL1 plus B2 DL2 plus B3 DL3, like that. You can continue like this till the end terms. Now here B1 is nothing but what is it? Because every loop last time we discussed that loop is nothing but magnetic field, means mu divided by 4 pi into 2I divided by R, okay, and into DL1, okay. Similarly, you can actually write a mu naught divided by,
B3 DL3.
yeah, it is B3, buddy. It is B3. Thank you. Which is mu naught 2I divided by R2, and the length is actually DL2. Similarly, there are so many steps you can actually write. So I would actually remove, now here you know that mu naught is common, 4 pi is common, and 2I is also common. And what are the things you have separately here? Which is a DL1 divided by R1 plus a DL2 divided by R2 plus a DL3 divided by R3, like that. So many things are there. Now, obviously from this one, mu naught divided by 4 pi into 2I. So you know that previously, what did I tell you, right? D1 DL1 by R1 is nothing but d theta 1. Yes or no? This is d theta 2. This is d theta 3. Like that, you will add up all the angles. If your angles are in a loop, whole angles, if I add up, what is the answer you will get it, right? If I add every angle, then it will be equal to 2 pi only, 360 degrees, right? All angles, if you in the loop, whatever loop it may be, if you just add all the angles, it will be equal to 360. So what I can get it here, this pi cancels, okay, this 2 and this 2 also cancels, and what is the only thing is remained here? Mu naught into I, which is nothing but your RHS. Note down. So you proved it, right? So you can write, hence proved, LHS is equals to RHS. LHS is equal to RHS. Guys, here, you know, in a CBSE wise, if I say CBSE final, they'll not ask you any, you know, the proof, so they will not ask you, but be prepared. Okay. Till now, they didn't ask any proof till now, but possibility is that they can ask you. So prepare well. This one or two times, if you prepare, it is easy for it. But application, they have asked n number of times. Okay. Today, I'll discuss 4 application, in which one is actually a NEET concept. Remaining 3 are actually CBSE. Right? Shall I move forward, buddy?
Just a second, sir.
Yeah, note down, no problem. And before application, I would like to give you few important notes actually. Next, buddy. Note, because note is important for us. So what is a note here? In the note, I am giving you sign conventions. Okay, sign convention I'll follow. For whenever I say sign convention, we'll always take into consideration of what, buddy? Coordinate axis system. So this is a positive x-axis. This is a negative x-axis. This is a positive y-axis. This is a negative axis. Yes or no? I think you are doing this from the childhood onwards. We are doing the same thing. So here also same here. What happens here? If I have two wires are carrying a current. So one wire is actually like this carrying a current. Another wire is going backwards. So due to this wire, there will be one magnetic field. Due to this wire, there will be one magnetic field. So what happens, buddy? It's like a bubble, buddy. Magnetic field is like a bubble. So what happens if the two bubbles come together? They will become a big bubble. Yes or no? So like that only. Here a big loop will form like this. Okay. These are all magnetic field only. So now you see, this is a, what I can say, this is a current I1 and current I2. So what is the Ampere circuital law will happen now? What is the Ampere circuital law here? You have to use a sign convention, which is B bar dot DL bar, which is equals to mu naught times I2 is going in the left direction. So it is negative. I1 is going in the positive direction. So can I write I1 minus I2? Yes or no? Right. This is, let's say, case 1. In the similar manner, if the wires are carrying a current like this, okay, one current is like this, I1, and this is a I2. Okay, magnetic field around this one is added. I told you, right? They'll add it like a bubble. They'll add and they'll become a big loop like this. I'm trying to show 3-dimensional because magnetic field is like a 3-dimensional. It will come around it like a disk. So now what you can write here? Here also integration B bar dot DL bar mu naught into, here I2 is actually going down, I1 is actually going up. So I can write I1 minus I2. This is your case 2. Tell me, any difficulty? Okay, shall I move forward?
Yes, sir.
Yes, sign convention is over. And one more note also you write down. Note, one more note. Yes, sir.
Yes, sir.
Yeah. And here a note here you write down, because I would like to compare Biot-Savart's law and this one, because very simple few steps I wanted to say. So you just write down a comparison between Biot-Savart's law, which I can say BSL, and ASL. ACL, is it okay? ACL means what is it? Ampere circuital law, right? Comparison between Biot-Savart's law, BSL and ACL. What is the comparison? So see here, there is a two comparisons are there. There are few things are similar, few things are different actually, right? So they'll ask you during your lab session, what is the difference between a Biot-Savart's law and what is the difference between Biot-Savart's law and Ampere circuital law, because these are important in the regular knowledge also you should have. So what is it actually? So I can actually say similarities. First learn what is the similarities between them. Okay, what are the similarities? First similarity I would like to give you that both relate magnetic field B and electric current and current. Is it okay with you? Because in the both the formulas you will find both the like both side you can actually see magnetic field and electric current. Because if you see for example here BSL, if I write what is a BSL, you write a dB is equal to mu naught divided by 4 pi, and you write a IDL bar dot cross R bar divided by R cube, R bar magnitude cube. And here also integration of this is a ACL. What is a ACL here? ACL is a integration of B bar dot DL bar, which is equals to, you write a mu naught times I. So what is a common thing you can see here? Here also magnetic field only you are finding. Here also magnetic, they are relating with the magnetic field and current. Is it okay? That's a similarity. Okay. Note done fast buddy. And next one is, what is that I can write here? Both expresses same physical, right? Same thing, right? Same physical consequences of steady current. When steady currents, they'll actually say I is actually here a steady current. Okay. So both will express same physical consequences with steady current. With steady current, both will give you same type of expression. Means here also it will give you magnetic field, here also it will give you magnetic field only. Both the formulas are meant to find magnetic fields only, right? So this is a similarity, but first similarity is that both will be giving a relation between magnetic field and current I. Let me write. So both will give a similarity that they will relate the magnetic field and current, and both gives the same expression. Okay, both will give us same consequences, physical consequences, mean same type of formula will they will give with the steady current. Any difficulty? This is a similarity. Then what is the difference?
So one.
Yeah, so one is actually in the differential form, another is in the integral form. That's a one difference. Second one is, let's write down, let's complete it. We'll go for the differences. Okay, shall I move forward? Differences. These are all asked for 1 mark, buddy. Mostly they'll ask you for 1 mark. Differences. So differences you can actually easily you can say. First thing is that ACL express magnetic field with the integral form, whereas BCL means BSL, not BCL, this is BSL, Biot-Savart's law, whereas BCL in a differential form. Right? That's the first difference you can say. Second is very important. It's asked many a times. What is it? See, second one is important. ACL means Ampere circuital law is based on electromagnetism. Whereas BSL is based on magnetism. This question they'll continuously repeat, buddy, because this law is actually based on electromagnetism, whereas Biot-Savart's law is actually based on the magnetism. Very important relation. This one is a very important difference actually. And third difference also very important. What is the third difference here? So here ACL is applicable for symmetric distribution of current. Symmetric distribution of current. If you have a symmetric distribution, a proper loop if it is forms, proper magnetic field it forms, then it is easier to apply the ACL. Otherwise, we have to actually use whereas BSL for what, body? Asymmetric application, asymmetric distribution. Distribution of current. I hope you understood what is the difference between ASL and what is the difference between Ampere circuital law and Biot-Savart's law. Biot-Savart's law is also gives you magnetic field. Ampere circuital law also gives you magnetic field. Okay, but Biot-Savart's law is only gives up when it will give you magnetic field when you have a symmetrical distribution, means there is no change in the current. You can actually apply ACL. Then only ACL is applicable. If there is a asymmetric, then it will give you a different. Okay, there I have to go with the BSL. This is the main thing. Both gives you magnetic field, both gives a magnetic field induction in relation with the electric current, both the laws. I hope you understood this one. Okay, but if there is a steady current, because for the CBSE we don't have a asymmetrical distribution, buddy. For the CBSE we have a steady current distribution only. So for a steady current distribution, both gives the same result, same type of formula both will give. Even if you apply BSL, if you apply ACL, both will give you same type of formula. Okay, so you can actually observe it with the cases. So can I go forward now?
Yes, sir.
Yeah, write down now special cases. Let's say application number 1. Application number 1. There are four application and related problems also we'll do today. Application number 1. So first application is a magnetic field B due to what is that here? Infinite long straight wire. Infinite long straight wire carrying current. Okay, magnetic B is nothing but magnetic field due to infinite long straight wire carrying a current. Okay, this is our first application. So what is the first application here? So what I'll take here, one wire I'll take here like this. Okay, to this wire I will try to draw a magnetic field. So with a different color I'll try to draw. So I hope it will be easy for you. The red color is a magnetic field. Think like this. Can you all okay with this? Yes or no? Chalo. So now let's say this is, let me just draw a little bit down so that you can understand. This is the center of it, and now anywhere the magnetic field is tangential to it, and what you take is one small length here, which is the point P you are taking, and this P here to here, what is the distance? Current inside this one, current I is flowing, right buddy? So here to here, what is the distance here? R distance. So just can you give me a minute? I'll draw a little big one so that you will actually visualize it. Okay. Okay, Ray? So here, let's say that now till here, this is a current I is flowing. This is a R distance, means this is a O center, and this is a point P. At this point P, you see the magnetic field is actually acting like this, means tangential to like this. This is like this. Magnetic field is like this, and the small length is also same direction it will act, which is a d bar. And here to here, the distance from the center to here, the distance is R distance. Okay, and this makes a loop. Now I have to apply here. What is that? I have to apply by ACL. What is that? Ray? Integration of B bar dot DL bar, which is equal to mu naught into I. Am I correct? So only one current, only one wire. So I only will come. So here magnetic field everywhere, anywhere you draw magnetic field is B only. Anywhere the magnetic field is B. And angle between them, you see the magnetic will B bar, and the small length on the this loop is same only. So which is parallel to each other. So angle theta will be 0 degrees. Now if I just continue here, integration, the dot product will give you what here? BDL cos theta, which is equal to mu naught divided by mu naught into I. So cos theta here, theta value is 0, cos 0 value is 1. Next, what happens here? B is constant, so B I am taking out. Integration here, DL into mu naught into I. So if I just integrate DL, means small length, if I totally add up, it will be equal to what? It will be equal to circumference, which is 2 pi r into mu naught divided mu naught I. Okay, so can I write here? Here I'll write. So B is equals to what can I write, buddy? Simply mu naught I divided by 2 pi r. If I just multiply 2 upside and downside, what happens here? Now it will be converts as a formula mu naught 4 pi into 2I divided by r. The same formula we have already found with help of Biot-Savart's law also. There also steady current only, here also steady current. So both will give you same type of relation. Note down. I can write one thing here. B is constant at every point. B is constant on every point of loop, and it is tangential. Note down.
Sir, how theta will be 0?
Because the element is also along with the magnetic field only, nobody. You see here, I'll try to show not there. Here also you can visualize. Here also, if I take a small element, it is parallel to it. Here also it is parallel to it. Yes or no? The small element is DL here. Here also it is. So you are actually taking the small element on the surface here, DL. DL is actually parallel to it. If it is a vector, then if it is a curve like this, right? Okay. So if it is the length is actually DL. But if you wanted to show vector means direction will be, what will you show? Direction will be like this only, no? DL bar. Yes or no? The small arc ray length is small, okay? But you are taking the vector, means you have to take a tangent only. So which is DL only everywhere. So it is parallel to this one. Everywhere it is parallel for the loop. Understood?
Yes.
Okay. Next, means this particular small element is it is on the imaginary loop. Okay, imaginary magnetic field is there, no? This is a loop actually. So on that a small element you are taking. Previously we used to take on the wire only, current element I used to say, with the Biot-Savart's law. There, that thing we are not following here. We are taking inside the loop itself, we are taking a small length. Okay, small portion of that particular loop you are taking it. Clear? Next is important one. Application number 2. Okay, magnetic field B due to current through a very long current through very long, sorry, not loop, very long circular cylinder. So magnetic field B you are trying to find due to due to current through a very long circular cylinder. So I'll take a cylinder now, very long cylinder. Okay, rod if you take. So that rod is actually circular cylinder, infinitely big rod, and now we are trying to find magnetic field expression for it. Right. So you have to solve it with help of two cases, not with one. You have to solve it with the two cases. So application number 1 has little bit complications here. Case 1 I'll say. What is a case 1, buddy? Simple. You have to take a cylinder. Let's take cylinder. This is a cylinder. Okay, a very big cylinder. And let's say like this, there is a cylinder. Now here to here, this is a cylinder, very big one, but one portion I can able to show you. or there is a, it has a axis, right? This is a axis. This is the axis. Now this axis I am taking it as a xy. Okay, one xy axis is there. Okay, let's say somewhere like this, one point, center C point I am taking. And now the radius of this circle is, what is the radius? Capital R. Okay, now what is the case one is actually, this case one is a point, let point P lies at the lies, you can say lies outside the cylinder, outside the cylinder. So the point lies outside the cylinder means the point, let me take the point P is here, which is outside the cylinder. Now this one, what is happens, buddy? So this is nothing but it will give a loop, right? A circular loop means like this, the magnetic field will form like this. Yes or no? There is like this, there is a magnetic field will form, and this particular point is actually, if I say clearly, this is actually located at the distance, how much here from this O point, it is at R distance. And now you can clearly say, what is it here? R is actually greater than capital R, means the distance is greater than the radius of the cylinder. And now one more important thing I should say, because definitely here inside this, the current is actually flows, current is actually flows along the axis. If it is a cylinder, current actually flows from the, exactly from the axis, from the central axis. Okay, draw the diagram first. So what is a magnetic field, buddy? Here magnetic field will be here everywhere, magnetic field will be, what is it? Tangent to it, which is, I can write a B bar, and even the small length is also along with it is same, only same direction, which is DL bar. So by ACL, by application of Ampere circuital law, what can I write? Integration of B bar dot DL bar, which is equals to mu naught times I. So next step, what is that? I can get it here, B DL cos theta, which is equal to mu naught times I. Next, already theta is 0 degrees because magnetic field is parallel to the DL bar. Then B will be coming out, and it is next, what you will get here? Integration of small dl, which is equals to mu naught times I. Integration of this one is actually what you will get, which is nothing but you will get a mu naught I divided by 2 pi r. It is equal to the circumference of it, and it is also, if I just multiply it and divide with the 2, it will become mu naught times 4 pi into 2I divided by r. So you have seen just now, just in last case, means the first case itself, you have seen that wire is also an infinitely long cylinder only, right? Yes or no? Then
Yes.
the expression, you see, same expression you're getting. Note down. Done, right?
So,
Finished? writing?
So,
Yeah, buddy.
so
Tell me.
yeah. In the last equation, you've written mu naught I divided by 2 pi r multiplied by like 2 divided by r equals to mu naught divided by 4 pi. So
Nah, beta.
how did
Nah,
4? Yeah,
Nah, it is 2 by 2, re.
2 by 2.
So 2
It looked
divided
like
by.
r, sir. Yeah.
Okay. Correct one. Very good observation. 2 by 2, buddy. It's not r, it is 2 by 2. Yes. Shall I go forward and write a case 2?
So 1 minute.
Okay. Next, in the case 2, what you do is you try to draw the separate diagram. Okay. Don't mix up like me. So case 2, here itself I'll try to make. So in a case 2, point P is now lying inside. Think that point P is lying not outside, but it is inside the cylinder. Then R is actually becomes, what is that, buddy? Lesser than the capital R. And the diagram also changes. You try to draw the separate diagram. I'll give you time, don't worry. So this is all goes the loop I have to take. Okay, sir. Right. Now you are taking a loop here inside it. Means that the loop is actually inside like this, it will come. Okay. So why we are trying to say here also, what happens, buddy? You know already, here also magnetic field is same direction. Even DL bar is also same direction. And it is located with the R distance, small r distance. Okay. Now, till here, so okay, but what is that I can get here? It is inside. The point is actually inside. If the point is inside, then it is not a mu naught. Definitely, it is having medium. The previous one is actually outside the cylinder, so I should write mu naught. But here I should not write like this. Here the few things will changes. Here I should actually take mu m. Means it is inside it. So permeable means mu naught is inside the m. So I have to say medium m. And the current actually here is it's not a total current is flowing through it inside this one. Let's say because you're taking a very small loop inside it. So current is here I dash, not the total current, but it is a partial current I dash. Clear? I dash. So got it, Ray. So this,
Can you explain again why is it I dash? I did not understand.
because it is not total current, buddy. It is very small loop you are taking, right? Inside it. So it is not total current passing through the total area. It is very small current passing through it. Okay, which is I dash, which is only from this small loop it is passing. So I dash only. If you take total, it is total. So here, one thing, because you will get one doubt. Why it is like that, sir? Because here, you see your consideration is inside. Definitely you have to take a lower current, not the higher current. So that's the reason I am taking I dash. But here one thing is constant. What is it? Current density is always constant. Current density J is constant. If it is constant, then few things will actually we have to consider. Means J is nothing but total current divided by total area of cross section, which is equal to partial current divided by partial area. This is a, let's say, total area, means circular area. This is a partial area. Yes or nobody? I can write here one step here. A and A dash are areas. Is it okay? So I is nothing but total current is nothing but what can I write? Pi capital R square. Here I dash is nothing but what can I write? Pi into small r square, because it is due to the loop. Clear? So this pi and this pi I can cancel. From this one, I dash is equals to, you can get it as a I into capital R square divided, sorry. I dash is equal to R square divided by capital R square. Is it okay? Let's take, this is your equation number 2. Any difficulty, please let me know. You
No, sir.
understood, right? Current density concept. Note down. I'll give a proper time. Note down it clearly.
Sir, but how can current density be same? Like, how can it be constant?
Sorry guys, there is actually a technical glitch. I hope the previous things are. Have you written everything?
Yes.
Yes, sir.
Yes, I hope you have completed it. So should I start from the, I'll do the derivation. I'll not.
Just the last line. Like the last.
I'll write that part. No problem. I'll write that. So I hope you wrote this one, right? So sorry, what is it? Right? Okay. Current
I
is
divided by
I divided by I dash divided by A dash. So from this one I can write I divided by A is nothing but pi r square, which is equals to I dash divided by A dash. A dash is nothing but pi small r square. So what I can write, buddy? Pi cancels. Then I dash is equals to, you can write clearly, I into small r square divided by capital R square. Yes or no? So here only one thing I would like to discuss. So this is, I have taken it as equation number 2, right? So now what I'll do is substitute equation number 2 in equation number 1. So what happens now? Equation number 2 in equation number 1, if I write, so what I can get it here, simply you can get it as a, so integration b bar dot dl bar, which is equals to mu m I dash. Instead of I dash, can I write I into capital, small r square divided by capital R square. Am I correct, buddy? So BDL is simple. Same step will continue again. So here it will be integration of b into dl cos theta, which is equals to mu m into I into small r square divided by capital R square. So here b will be constant everywhere. Cos theta, theta is 0 degrees. Can I write again? So if I write theta is equal to 0 degrees, right? And integration of dl will be left here, and mu m into I r square divided by capital R square, right? Now if I just integrate all the things, that will be equal to, what is that? That will be equal to mu naught divided by, this is equal to, what is it, right? 2 pi small r, right? Again you have a I into r square divided by capital R square. Understood, right? This entire value is equal to, what is it, right? This entire value is equal to 2 pi r. It will come down. So now you know that r and r can cancel one time. So what is the left out part? This is mu r m, buddy. So what is the left out part here? Mu m divided by 2 pi into I divided by I into r divided by r square. Am I correct, buddy? So next step, you can actually divide, multiply and divide with the 2. So the form will be converts as a mu naught divided by 4 pi into 2ir divided by capital R square. Am I correct, buddy?
Yes, sir.
Yes or no? Here, one thing I would like to ask, like
So
previous
mu
one,
m.
this is mu m, buddy, not R. This is mu m. This is mu m, sorry. So mu m is equal to 4 pi into 2 pi r 2i r divided by 4 pi into r square. So here one simple thing I would like to say, here b is actually directly proportional to r. Here in case 2, b is directly proportional to r. In case 1, you see, in case 1 you write b is inversely proportional to r. I'll discuss that. Just note down this one. Finished? Okay, guys, let's just see the next step because I'll try to plot a graph here because graph is important for us. Here, in a case 1, what you got it in case 1? B is equals to, you got it as mu naught divided by 4 pi into 2I divided by R. Am I correct, buddy? In a case 2, magnetic field you got it as mu m into 2I into R small r divided by, here is 2 pi, means 4 pi into capital R square. So you can clearly see magnetic field, and here what is the relation, buddy? Magnetic field is inversely proportional to R. Yes or no? And one more thing I can actually say, what is it, Ray? So you know that mu m, mu r is nothing but relative permeability. If I say mu m divided by mu naught, so from this mu m is equals to, I can write mu r into mu naught. So this formula will convert into what here? Mu m divided, sorry, instead of mu m I can write mu naught divided by 4 pi into mu r 2ir divided by capital R square. So here you have seen that even if it is looks like very big, so here you can see magnetic field and the radius means the distance is actually direct. So here I have a directly proportional to R. So inside the cylinder, magnetic field will be increases as the distance increases away from the center of that axis. But here it is outside, it is inversely proportional. So if I try to draw a graph here, so this type of graph you have seen already in the gravitation chapter of first year, and in this also in the first chapter electrostatics also you see this is R, this direction. So if I say, if it is equal to small r is equal to capital R, this is a line if I draw. So now what I can get it here till here, if I say it is a lower than, R is lesser than, here this region is actually directly proportional. You will actually get a directly proportional, a line you will get it. But here you will get a inversely proportional. This is a magnetic field is directly proportional to R, it is a inversely proportional to R. When it will be inversely proportional? If R is here, R is actually here lesser than capital R, where R is greater than capital R. Have you seen this graph somewhere? In a Gauss law we have seen, right? Whenever you do the sphere, inside the sphere what is the electric field, on the sphere what is the electric field, outside the sphere, like that. This is also like that one.
Can you break for some time?
Yeah, buddy. You want break now? Take it. What is the time now? Okay, take a break, buddy. Come back by 9:14. Okay.
Thank you.
Thank you.
Yeah, buddies. Next, do one example. Okay, then we'll study other applications. Okay, chalo. Example now. A long straight solid conductor, solid metal rod of radius 4 centimeter carries a current 2 amperes uniformly distributed, okay, over a uniformly distributed over its circular cross section. Find the magnetic field induction. Find the magnetic field induction at a distance 3 centimeter from the axis of the wire. From the axis of the wire. So see here, this is a question. So inside this one, you can clearly see this is a case 2 question, where you see this is a straight solid metal rod, radius is 4 centimeter, carries a current is 2 amperes, uniformly distributed over its circular cross section. Find the magnetic field induction at the distance is actually 3 centimeter from the axis, right? So it is very clear that capital R is here 4 centimeter, means 4 into 10 power minus 2 meter, and small r is actually here 3 centimeter, means 3 into 10 power minus 2 meter.
What
Now
is
you
it?
see,
Find the magnetic field induction.
yeah, induction at distance 3 centimeter. And you can clearly see R is actually lesser than capital R. R is lesser than capital R. And one more thing, if they didn't give mu R value, you have to take mu R value is 1, right? Let's try to solve it here. Magnetic field is what is that? The formula you have right here, that is mu naught mu R divided by 4 pi into 2I small r divided by capital R square. I think this is the formula, right? Yes or nobody? So mu R value they didn't mention in the question, so you can take it as a 1. And mu naught by 4 pi. So this is mu naught by 4 pi. Value is how much? 10 power minus 7. 10 power minus 7. Mu R value is 1. Let mu R value is 1. So let's take 1. 2 into current passing through it is how much better? What is the current here? Current is actually 2, and radius is how much here? 3 into 10 power minus 2 divided by what is the capital R? 4 into 10 power minus 2 whole square. Yes, give me the answer. Which will be Tesla, or you can say Weber per meter square. In chat box, give me the answer.
Three into 10 raised to the power minus 5.
Okay, buddy. No, check your calculations. Here it is square, buddy. At the down, it has a square. You're not squaring it. Whatever you said is actually without a square. but at the denominator it is squared. Tell me,
can
Ray.
you,
3/4.
Yeah, 3/4 is nothing but how much? It is 0.75. 10 power minus 5. Buddy, your voice is not clear.
sir,
What
can
did-
you hear me?
Yeah, tell me what happened.
Sir, can you tell me about the mu r? So I couldn't listen to that time.
Yeah, mu r is actually a relative permeability. It is actually equal to 1. Okay, you have to see this as a, if they are not given in a question, generally they'll give it a nearby, like in bracket, they'll mention what is a mu r. If they are not mentioning, you have to take it as 1. Okay.
Thanks. Yes.
Generally they'll give you some value here, they'll give you some value, but if they are not giving, you should actually keep in mind that it is 1, right? Simple only, there is no big issue, you can actually do all these things. Next, put next heading is application number 3. Solenoid. Application number 3, solenoid. Number 3, solenoid. Very important one, because not only this chapter, the upcoming chapters also, solenoid plays a crucial role. So you should have a proper knowledge over it. So application number 3, this solenoid. Right? So you know that what is a solenoid? Solenoid is like a helical structure like this. Yes or no? The wire is actually winded, helical structure, and in between these two, what is that? You will always have a, here you will actually place a, a gap in between. This is a gap, right? So this gap will actually fill with the insulator. Sometimes insulator you can fill, okay, insulator if you fill, or sometimes a conductor, or sometimes it's a vacuum also, right? So you know that what is a solenoid? Solenoid is simple, that you are actually winding the wire. It is on the circular cylinder. You can say it is on the conductor, or else on the insulator, or else on the, normally it is just left like that only. It is maybe a vacuum. Is it okay? Now, if I say solenoid, so simple here, solenoid, let's suppose the current I is passing through it is like this. Current I is actually going through this one is like this. Now, when you section the solenoid, what will actually look like? Okay, when you section the solenoid, so I'll try to draw. So first we'll understand how it will give the magnetic field. Okay, so the magnetic field is here, let's say here 2 points I will take like this. Okay, now think that actually current is going inside like this and coming out. Okay, so here from down, say from this one it is going like this, current is going. Now what happens, buddy? It will go inside and comes out like this. Okay, next like this, next like this, next like this. This is a wire. Yes or no? Can you just understand what is it? It is a wire which is actually helical. Only one side I can show, other side is inside the screen, right? So current I is actually, it's flowing like this. Now what happens, you know that here current is actually going inside here. Yes or no? So when current is going inside, then I should actually take right hand thumb rule, place your thumb inside the screen and you roll it. So magnetic field around this one is how is it actually flows? So magnetic field, if I try to see here, each will give you one on one loop. I'll try to draw. So here the current is going inside. So magnetic field is clockwise or anti-clockwise? Tell me, Ray. It is clockwise because you will roll it like this. Can you see the hand on the screen? It is rolling like this. Yes or no? It is clockwise. Yes or no? Here also what happens, it is current is actually coming out of it. Current is actually coming out of it. And current is coming out of it. Then here also small loop will form, magnetic loop. Current is coming out of it. When current is coming out of it, thumb is actually towards you and it is curling like this. Means it gives you anti-clockwise. Yes or no? So here I am trying to write like this. This is a anti-clockwise. Here it is anti-clockwise. Now you see here, whenever these loops are becomes bigger and bigger, I told you the magnetic field is like a bubble. Okay. So now one more loop, if I take it from here, a big loop, if I take it, what happens? It will add this loop also, and this loop also, this loop also, and becomes a very big loop, a very big bubble it will become. And it is of how much here? It is clockwise or anti-clockwise? It is anti-clockwise. This is clockwise. Okay. And here also one bubble will form upper side like this, a common bubble. Okay. And it is like this. It is anti-clockwise. So inside this one, you see arrow marks, they are actually showing a very near loops are actually, the lines are very near to each other. And here you can see one more bubble, if I take one more loop, if I take it, this will be like this, and this is actually going inside. And here also, if I take one more loop, because you have to take a symmetric loop, buddy. It's a freehand diagram, so I am trying to draw the loop. So you can see here magnetic field lines, this one, this one, this one, this one, all the three lines are. So here you see magnetic field direction inside the solenoid is in like this, and outside this magnetic field lines are broader and broader, but inside the field density, means the magnetic field line density are more inside that. So magnetic field will be stronger inside the solenoid. Yes or no? It will be a uniform magnetic field. So if I say similar diagram, if I try to see on the this dotted lines, I'll try to draw with the dot lines like this. Here also this is dot line, and the magnetic field line visualization, if I do, so this is like this. This is also like this, straight line. And then if I try to draw here, there is a loops. Right? Draw it. This is the magnetic field lines of solenoid, which is like bar magnet. Which is like a bar magnet. So which one polarity? Can you able to tell me which side is the polarities? Because it is inside the magnetic field is going. So this side it will be south pole, sorry, and this side it will be north pole. Yes or no? From north pole, field lines will come emerge out, but in south pole they'll actually go inside. They'll form the loop. So the magnetic field lines of solenoid will be like this. It looks like this. Okay. This is a proper visualization. Any difficulty, please let me know.
Yeah, sir. One doubt I have.
Yeah, buddy, tell me.
So, from which side was they attracted? Like south, north, and south, sir. Because the solenoid is hard. It's hard to define which is north, south. Sir.
You can find, but it's not a big issue. You have to see which side the current direction is going on. Based on that, you can actually say. Can you able to say now? because inside this one magnetic field lines are going, right? Inside that they are
Yes,
going
sir.
this side. So this would be south. This is south only. This is north. Because solenoid behaves as an electromagnet, right?
So
Yeah, buddy.
I have doubt in the direction of magnetic field.
Yeah, very simple, buddy. Can you just see this one, the red line, whatever I drew?
Yes, sir.
Now see my face. The finger is actually, the thumb is actually, you have to inside. Yeah, it is actually inside. And now you have to rotate your finger. Got it? Right hand thumb rule. I should use basically right hand thumb rule.
Okay.
Okay. Now, whenever you see upper part, current is emerging out of it. So it will be, thumb is actually towards you and you have to rotate the fingers, curl your fingers.
Oh, yeah.
So it
The
will be,
magnetic field lines always travel from south to north.
what Ray? Which school you are studying, Ray?
No, I'm asking, sir.
Don't you know that inside the magnet is south to north and outside that north to south? Nobody. बचपन का क्वेश्चन है रे ये. Who is that? What is your name, Ray? Okay, leave. You understood, right? Actually, it is inside like that. No need to worry. You will actually understand more and more about it in upcoming days, because most of the the upcoming 6th chapter, especially 6th chapter, is about the solenoid only. So you should be very, very careful with the solenoid. Right? If it is a bar magnet type, so what is that? This loop will look like simple here. Loops are there, no? So north pole, from that loops will come out. From south it is goes in. So inside that south to north, outside it is north to south. So it is not about a polarities now. It is about a magnetic field. So magnetic field is actually what happens inside this one. South to north actually happens. So polarities are not important in this chapter. But remember it, even you should actually have a knowledge over polarities also. So this is what the magnetic field lines look like. But our main intention is that we need to find magnetic field expression for the solenoid. Okay. Okay. Let me go with the next one note you write down right here. Magnetic field lines, magnetic field B of solenoid, magnetic field of solenoid at the outer point outer points is negligible due to magnetic field lines are repulsed each other.
So 1 minute, could you go back to the previous slide?
Okay. So magnetic field, if I say outside the solenoid, do you see the magnetic field lines are actually very feeble, means they are actually very broader and they are actually going away from it. But inside that they are actually very near to each other. Okay. So that's the reason I can say, that's the reason, what can I say right here? The solenoid outer points is negligible due to the magnetic field lines repulsed each other, right? But next one more point you should write here. But inside here itself you continue, but inside magnetic field lines, no need to write magnetic field lines, you already understood. But inside magnetic field is uniform and stronger as compared to outer side. due to number of due to number of field lines. Okay, number of field lines very closer to each other. Let's say closer to each other. Can you understand? This is a simple way, because magnetic field outside the solenoid is 0. Okay, and inside the magnetic field lines is stronger as compared to the outer side, due to the number of magnetic field lines are closer to each other. When this thing happens, when solenoid is tightly wounded. Okay, all the condition I'm explaining in the one point itself with a broader point. Okay, so when the solenoid have a wires, they are winded very closer. Outside point magnetic field will become 0. Inside you have a magnetic field stronger one. Okay, clear? Note down this one. This is very important. Completed. Write faster because time is ticking. Next, see here.
So 1 second last.
Azam, right? Flash, are you there? Flash.
Thank you.
Okay, right. Chalo, we'll try to find a magnetic field for it. So you see here the solenoid is, I'll try to draw the cross-sectional diagram. Okay, means cross-section in the sense you are cutting it, and if you see the diagram will be looking like this. Shall I draw a little bigger? What has happened? So this is the lower part of the solenoid, and that is upper part body. And I'll try to draw the small boxes. Why like that? Here, these boxes indicates wire is going in and coming out, and this solenoid is tightly wounded. Right now, it is going. Let's suppose it is going inside. Here it is, wire is coming out, and here is wire going in. In means you have to draw with a cross. It is coming out. Okay, there is a very big derivation, but I would like to make it short. Right. So now what happens, buddy? Now field lines will go. These are all, whatever the blue lines I'm showing, these blue lines are all field lines, magnetic field lines. Magnetic field lines. Right. Now what you take is, you have to take a one loop. Okay, one loop you try to take, buddy. The loop is actually anywhere you can take. So I'm taking it here I'm taking. So the whatever the green line I'm drawing here, a square loop instead of a circular loop, I'm taking a square loop. Okay, and this loop is actually, you can see I'm naming it as a P Q R S, and the length of this one is a square one L. Right. What is that? What is that I have to do? By application of, by ACL, by Ampere circuital law, what is that? Right? Integration of B bar dl bar, which is equal to mu naught into, because here number of wires are winded, ऐसा no, thread in a starting of the class only I told you that here it is current is actually the wire is threading now. So threading, then here what should I actually write? Here there is one term called N will come, I will come, and length also comes. Means N into only two terms are extra here. N is the number of turns. I'll tell you what is the N and all. N is the number of turns, means number of lines are actually winded inside it, and it is the total. L is the length of the solenoid. Okay. So now this is what is the loop actually. Loop you are following is PQRS. Total loop is PQRS. Right. Now, one thing I would like to say here, what I can do is I can actually expand the loop. Means this loop is P to Q, you will do the integration Q to R and S, R to S and S to P. So you see here integration, okay, P to Q B dl cos theta plus integration Q to R B dl cos theta plus integration R to S B dl cos theta and continuation plus integration S to P B dl cos theta, which is equals to mu into I. So you already right, you already have a I, then one more term you will actually add N into L. N is the number of turns. I'll tell you what is N and all. So now what happens here, see Ray, just listen here. BPQ, it is actually parallel, right? So angle is how much here? What is the angle you have? Angle is actually 0 degrees. Here Q to R, anywhere if you take magnetic field lines are this type and the element is actually 90 degrees. So here angle is actually 90 degrees. And but you see R to S, R to S is actually outside point. But here what happens here? Magnetic field itself becomes 0. Similarly, here also angle is how much here? Angle is 90 degrees. Then what happens? Everything. Now, due to this one, this entire term will become 0. This will also become 0. This will also 0. Only this one will be there, which is B will be taken outside. Integration P to Q, angle theta is 0, means cos 0 is 1. Then which is dl, which is equals to mu naught into I into NL. Okay, then if you integrate it, you will get a length, means small length. If you take the small length here, so how will you take a length? Length means a small length here like this, dl length. So this length, if you take all this, it will be equal to length L only, which is B into L, which is equal to mu naught into I into N into L. This L and this L cancel. Magnetic field is equal to, what is the formula? You will get it, mu naught into Ni. It's a simple way of derivation. Not done. Water. Then
Yes, sir.
finish, buddy. B is equal to mu naught into N into I. Just we'll go a little forward now.
So 1 minute.
Okay, note.
So how did you integrate from P to Q, sir?
P to Q, actually here to here, what is the length?
So what about R and Q? R to Q.
They are perpendicular, right? Q to
Oh,
R is
okay.
S to P is perpendicular. QS R to S is outside, so magnetic field is 0.
Yes.
Okay. Chalo, few notes we'll write. Note. Note is important. Okay. What is the note, buddy? First note is that what is here, B is equals to, I told you that mu naught into N into I, right?
Sure.
Yeah, buddy.
So could you show the PS right? Thank you, sir.
Yeah, buddy. Chalo. Here mu naught into Ni. Here you know what is I, what is mu naught, but N is nothing but here N is equals to, there is a formula called X into N divided by L. Number of turns, here N is nothing but number of turns. Capital N I'm writing, it is number of turns. X is nothing but number of folds. Folds means first time you did actually one winding ray like this. Then in one more winding you have done like this, double. Then how many folds are there? Here X value is 2 folds like that. And one more thing here, L is nothing but what is it? Length of solenoid. Okay, remember this formula, very important. And then a second one, what is it? Now, okay, if this magnetic field is, what is it? This is inside the solenoid. Actually, magnetic field inside the solenoid is mu naught Ni. If point P at the edge of the solenoid, then what is the magnetic field? Magnetic field now becomes mu naught Ni divided by 2. Mu naught Ni divided by 2. Remember this formula. And then now there is a last application is a toroid. What is it named? The toroid. Application number 4. Name is toroid. Okay, buddy. Toroid. Toroid is a simple here. Toroid is like solenoid, but solenoid is actually having ends. It does not have ends. Okay, the ends is actually like this. Right? So you will actually take one of the insulator, or you can say a conductor is like this. First level, first loop, and then the second loop. Is it clear with you? First loop, and this is a second loop. Now what you are trying to do is you are trying to wind a wire. Let's suppose the wire is actually winded like this. So you have started a wire, one wire is going like this, one wire is coming out. So let's suppose like this, it is going winded, okay, totally winded. Like this, the winding is there, okay. Here thing is that, let's suppose it is coming out of it and it is going in. Can you understand this one? Okay, like this the windings are there. This is the structure of toroid. So if I try to draw the diagram for it, it is similar, because now cross-sectional diagram is important for us. So what I'll try to do is, first let me draw this entire structure. So this is the inner structure, okay. Right. This is the first coil you should, because the base of this one is this one. And then what I'll do is one dotted line. Now first I'm doing the red color wala. So it is for this one, you will have a dots like this. This is a, so current will only pass through this axis of it. It's not a donut, but the current will actually pass through the axis of the coil, okay. So this coil from the center, it is located from the center r1 distance. Think like that. Next, now you see current is actually going in, so wires actually going inside. Let's think that current is going inside. So inside every point you have a like this. I'm trying to draw the the black color dotted lines where wire is actually going inside. Okay, so can I show with the dot? These are all dots. Outside wire is coming out, so I will show with the cross. Like this, the wires can show up, which is a cross. Right, buddy? So this loop, again, you can see this cross marks is actually makes one loop. These are anyhow outside, and this is located from here. Can I draw this one? Is actually this loop is located. Distance is here R3. Let's take it is in outside, it is R3. This is R2, let's take. And inside, whatever the dotted lines are there, no? Inside the dotted lines, if I join them like this, this is also shows one loop. So this loop I am it as a R1. So outside this coming out and in wires are there, no? That is weight you have to take. Then simple here by ACL means Ampere circuital law. What you are going to do here? The loop here means everything, every loop you are going to take integration of loop 1 b into b bar dot dl bar. Let me take like this, plus integration loop 2 b bar dot dl bar, plus integration loop 3 b bar dot dl bar, which is equal to same body mu naught into I into here n into I, n into L, length of that wire. Any difficulty now? So loop one is actually inner line. So this whatever the current is going, no, these are all loop one. So this loop one is actually, you see, for the solenoid, if I just solenoid, right? So wire, this is the solenoid, no? If I join like this, sorry. So this is a solenoid. I told you the solenoid outside part. This is a toroid looks like actually. So solenoid, this is also outside, this is also outside for it. So here what happens, loop one means R1 wala. So this is also becomes what here, magnetic field is actually B1 is 0 for it. And loop 3 is also lies outside. For inside the toroid, magnetic field is 0. Outside the toroid also, magnetic field is 0. This is B3. Let's take this is B2, L2. This is a B3, L3, B3. Is it okay? So B3 is also 0. Here B1 is also 0. Inner also 0. Outer also 0. Because solenoid outer surface is 0, right? So similarly, in the toroid, inside and outside, it will be 0. Only thing is left this one. So if I say, note down fast. Now here, what I am taking in this case, where B2 is equal to total magnetic field B. So what I'll get it here simply, what I can get, B is equal to integration of loop 2. And this is a DL2 is nothing but DL2 I am taking. And which is equal to mu naught into NIL. Right. Next, whenever you integrate, this will be equal to B is equal, so it will be equal to L, where is equal to mu naught into N into I into L. So where happens here, L and L get cancelled. This is also equal to the magnetic field also, the expression is same like a solenoid. Right? That's all for today, guys. Okay.
Sir, can you show the last slide?
Okay. Thank you, guys. I'll see you in the next class. So this is the 4th application. Yeah, buddy. Good night.
Thank you, sir. Bye,
you.
sir.
Bye
you, sir.
bye.